Inside the microcontroller, let's look more closely at the address bus. The address bus answers one simple question: where should we go? The address bus carries addresses from the CPU to memory or to peripherals. It tells the system exactly which location the CPU wants to read from or write to. Notice something important. The address bus does not carry the actual data. It only carries the destination. A good real-world analogy is a road sign. A road sign tells you how to get to goal or matara, but it does not carry your car or your passengers. It simply provides the direction. The address bus works in exactly the same way. The CPU places an address onto the address lines, and the rest of the system knows where the operation should happen. In most microcontrollers, the address bus is one way. Information flows from the CPU outward to memory and peripherals. The CPU is the decision maker, so it tells the system where to go.
Another important concept is the number of address lines. If a system has n address lines, it can access 2 to the power of n different locations. For example, with 4 address lines, we can create 16 different addresses, from 0 to 15. With 16 address lines, we can access 65,536 different locations. And with 24 address lines, the number becomes more than 16 million locations. So the wider the address bus, the more memory and peripherals the system can manage. Of course, the address bus does not work alone. It works together with the data bus and the control bus. The address bus says where. The data bus carries what. And the control bus tells the system how and when the operation should happen. The big idea to remember is this. The address bus is the pathfinder of the microcontroller. It tells every part of the system exactly where to go. Without addresses, the CPU would have no way to find the information it needs. No address means no access.
We have already learned that the address bus tells the system where to go. Now let's look at the data bus, which carries what is actually being transferred. The data bus carries the real information between the CPU, memory, and peripherals. This information can be numbers, letters, commands, sensor readings, or calculation results. Unlike the address bus, the data bus works in both directions. Data can travel from memory to the CPU, or from the CPU to memory and peripherals. You can think of it as a two-way highway. Vehicles can move in both directions, carrying important goods to different destinations. The data bus works in exactly the same way. During a read operation, the CPU asks for information. The memory or peripheral then sends the data back to the CPU. In this case, the CPU is the receiver. During a write operation, the CPU sends information to memory or to another device. Now the CPU becomes the sender.
Another important concept is the width of the data bus. The width simply means the number of data lines available. An 8-bit data bus has 8 lines and can transfer 1 byte of information at a time. A 16-bit data bus can transfer 2 bytes at once. A 32-bit bus transfers 4 bytes, and a 64-bit bus transfers 8 bytes in a single operation. The wider the data bus, the more information can move during each clock cycle. That is one reason why modern processors can perform tasks so quickly. For example, an 8-bit pattern such as 10111001 represents 1 byte of data. That byte could be a number, a letter, a command, or a sensor value. The important point is that the data bus carries the actual information that the system needs to work. So remember the difference. The address bus tells the system where to go. The data bus carries what needs to be sent or received. Together, they make communication inside the microcontroller possible. The data bus is truly the highway of information that keeps the entire system running.
Before we move forward, let's pause and look at the mental model we have built so far. For Arduino projects, this mental movie worked extremely well. It was simple, clear, and very powerful. We knew that the ATmega 328P was the brain of the system. We understood that flash memory stored our program permanently. We knew that RAM stored variables and temporary data while the program was running. We learned that peripherals handled special tasks such as timing, communication, and analog measurements. And finally, we knew that the input and output pins connected the microcontroller to the real world. With this understanding, we could build many useful projects. We could blink LEDs, read push buttons, measure sensors, display information on an LCD screen, drive motors, and even create sound and motion. This mental model worked well because it was simple.
It allowed us to predict what would happen when we wrote a program. And most importantly, it helped us build real systems that actually worked. But now we are beginning to build larger and more intelligent systems. Robots, smart machines, industrial automation systems, and connected devices. As systems become bigger and smarter, this old mental movie is no longer enough. We need to zoom out and see a much bigger picture. We need to understand not only the building blocks themselves, but also how information moves between them and how they cooperate as a complete system. So the big idea of this slide is this. Our old mental movie was correct and extremely useful. But now it is time to expand that picture and develop a deeper engineering understanding of what is happening inside the microcontroller.
Now we are ready to see the bigger mental movie. A real microcontroller is much more than a simple black box. It is actually a complete mini-computer on a single chip. Many different building blocks work together at the same time. At the center is the CPU, the brain of the system. Inside the CPU itself, there are even more specialized components. The ALU performs calculations. Registers provide extremely fast temporary storage, and the control unit coordinates everything that happens inside the processor. On one side, we have memory. Flash memory stores our program. RAM stores temporary data and variables. And EEPROM stores important information that must survive even when the power is turned off. On the other side, we have peripherals. Timers keep track of time. The ADC converts analog signals into digital values. UART, SPI, and I2C allow communication with other devices. PWM controls motors and power, and watchdog timers help keep the system safe and reliable. But the most important idea is this. All these building blocks are connected by information highways called buses. The address bus answers the question, where should we go? The data bus carries the actual information. And the control bus tells the system how and when operations should happen. Finally, the I/O pins connect everything inside the chip to the outside world. Through these pins, we receive button presses, sensor measurements, communication signals, and many other inputs. And through these same pins, we control LEDs, motors, buzzers, displays, and external devices. This bigger picture allows us to build amazing applications. Home automation systems, smart robots, medical devices, industrial machines, drones, smart agriculture systems, Internet of Things products, and even electric vehicles. So the key message is simple. Information moves. Everything connects. Everything works together. When you press a button, a complete chain of events happens inside the microcontroller. The signal enters through a pin. The buses move the information. The CPU makes decisions. Memory provides instructions and data. Peripherals perform specialized tasks. And finally, another pin produces an action in the real world. This is the real power of microcontrollers. Zoom out. See the connections. Visualize how addresses and data move between separate units under the control of the program you wrote.
Let us build the mental movie. We are no longer looking at individual parts in isolation. We can now understand how everything connects and how information moves throughout the entire chip. Flash memory stores our program permanently. RAM stores the variables and data that the program is using right now. At the center is the CPU, the brain of the system. The ALU performs calculations.
Registers provide extremely fast storage for immediate work. The control unit coordinates every operation. And the clock system provides the timing that keeps everything synchronized. Further, we have the specialized workers called peripherals. Timers count time and create events. The ADC converts analog signals into digital values. Communication modules, such as UART, SPI, and I2C, connect the microcontroller to other devices. PWM generates signals to control motors and LEDs. Watchdog timers improve safety and reliability. And GPIO ports manage the input and output pins. Connecting all these building blocks are the buses, the information highways inside the chip. The address bus answers the question, where should the information go? The data bus carries the actual information in both directions.
And the control bus carries commands such as read, write, clock, interrupts, and reset signals. Finally, the I/O pins connect the microcontroller to the outside world. Digital inputs receive signals from buttons, switches, sensors, and encoders. Digital outputs drive LEDs, relays, buzzers, and motor controllers. Analog inputs measure temperature, pressure, light, and other real-world quantities. Analog outputs generate signals for audio and actuator control. And communication interfaces connect the system to computers, networks, and other intelligent devices. Let us follow one simple example. Suppose we want to read a button. First, the CPU places the button's address on the address bus. Next, the control bus sends a read command. The button state, either 0 or 1, travels back on the data bus. The CPU receives that information and uses it in the program. Then the entire system continues running millions of times every second. Close your eyes. Imagine what is happening in the microcontroller. This is the foundation of all embedded systems. Once you understand this complete mental model, you can understand, debug, and build almost anything based on microcontrollers. And this bigger picture will stay with us as we move to more advanced systems in the future.